Okay, everybody. So in this video, I need to tell you something about how derivatives relate to spoken information about how fast something's happening or how something's moving. Okay. So I'll give you this example to think about in the context of what I want to tell you, and then explain how calculus is going to fit into it. And then maybe you can recognize some of the same verbiage in problems, and then you'll understand that this is the context that it happens in. So let's say that there's this common point of reference and a person walks to the left at a constant 4 feet per second. Okay. All right. Constant, meaning no speeding up, no slowing down. All right. Now, when we say that something is happening at a constant rate, what that's going to end up meaning is that in this case, the variable a, which is the distance from here to wherever the person is a linear function of time, okay? 4 feet per second, distance over time. So, all right, they're going that way. They may be moving 4 feet per second, but let's say for the sake of doing some math at some point, we'll say that their position is this point with respect to there, okay? All right, now then say there's another person and that with respect to the same point, they're going this way on a bike, 25 feet per second, okay? And suppose that's constant, a constant rate of 25 feet per second, meaning no slowing down, no speeding up. Now again, if I tell you that that's constant, a constant rate of 25 feet per second, that's going to mean that b is a linear function of time. B is this side of the triangle. It's the distance from here to there, okay? So I would imagine that as the person walks, this side of the triangle, side A, gets bigger, and this side of the triangle, side B, gets smaller, okay? Now what I'd like you to do is calculate the derivatives, dA over dt and dB over dt, okay? So for that, the instantaneous rate of change of side B with respect to time, dB over dt, and the instantaneous rate of change of side A with respect to time, dA over dt, those are included in the description, okay? You don't really have to do any math. I'll show you why you don't have to do any math, but if you're happy just accepting that that's true, if something is happening at some constant rate, then that rate is the derivative. Okay, so I've said it there. That's how it works. But what might be a little harder to understand and what you might overlook from now on into the future is that this one would be negative and that one will be positive, okay? The simple reason for that is because as the person on the bike goes this way, side B is getting smaller. Maybe they're moving an absolute 25 feet per second through space, but if I'm tracking their location by way of this side of the triangle, then B, all right, is getting smaller as time goes bigger. Okay, so that one's negative. So any derivative will be negative if this variable on top gets smaller as that variable on the bottom gets bigger. Okay, but in the sense that, as I told you, if that's a constant rate, then it is the derivative. Okay, dA over dt. Okay, that's going to be 4. Why? Well, because they're walking 4 feet per second. We track their movement as side A of the triangle is going to get bigger. Okay, so the fact that that derivative there is positive, that means side A gets bigger as t gets bigger. Okay, so this one's negative, that one's positive, all because the variables involved are either getting smaller or bigger with respect to time. All right, so I just needed to tell you that. You can accept it if that's the way you are and you don't need an explanation any further, then that's great. But I thought that I should include more explanation in case that's what people want. So think about it like this. What do we mean if there's a constant rate of 4 feet per second? Like, what would that look like? So for example, look something like this. Let's say at time t is equal to 0, that A is 19 feet, meaning that at some time t is equal to 0 from here to there is 19 feet. Then if you're moving at a constant 4 feet per second, that means no slowing down, no speeding up, then, well, that means after 1 second, you'd have to be 4 feet further down. So it'd be from 19 to 23. And then another second after that, you have to be 4 more feet. So that means 23 to 27. What did I do here? Half of a second? and 2 feet, is that the same thing? Is moving 4 feet in 1 second, 4 feet per second, the same thing as moving 2 feet in half of a second? Same thing. Take 29 minus 27 feet, that's 2 feet, over half of a second. Okay, there's your average speed right there. It's 4 feet per second. Okay, so that's what we mean when we say that it's linear, something like that. Okay, that's just an example. You can say, how do you know is it 19 feet? I could have used any number and gone with it from there, and it would have worked out the same way. B, all right, so say at time t equals 0, b is 100. Okay, so this is 100 feet from here to there. So you're going that direction, 25 feet for every second. So after 1 second, where are you going to be? Further up, so b is going to be smaller. So b might be, say, if it was 100 originally, 1 second later, 75. And then another second, 50. And then another one, 25. So what's the average there? Say, like right here in this interval, what's your delta b over delta t? 25 minus 50 over 3 minus 2. Well, that's negative 25 feet per second. That's why it needs to be negative. B's getting smaller as t gets bigger. It would look something like this. Maybe the numbers would be different, but it would look something like that. The math would work out the same way in the end. But that's all based on the assumption that that's a constant rate of 25 feet per second. So why can I use the deltas to justify my answer for the derivatives? Well, remember that in another video, and which I've tried to bring this point up many, many times, we said that a derivative, for example, dy over dx would be equal to delta y over delta x if what? We have a linear function. Okay? If we have a linear function, if y is some linear function of x. And when I tell you that this rate or that one is constant, what it means is that these variables are linear functions of time. Okay? So it's no surprise that any way I try to look at this from whatever vantage point, I'm going to get those as my derivatives from this initial information. All you have to do, really, when you read something like that, is think about, well, I know my number, 25 and 4, but is b getting bigger or smaller? And is a getting bigger or smaller?